pleased to introduce our speaker, Rebecca Steiner. She's now at Vanderbilt University in the logic group there. Before that, she took a PhD last spring from the Graduate Center at the City University of New York. She was a student of Russell Miller there, who I think is known to maybe a couple people in the department and has visited with us before. Rebecca's going to talk about the question of whether it's harder to factor a polynomial or to find a root of a polynomial. We look forward to hearing what she has to say.
Wherever you want.
Okay, so the basic question that we're going to be addressing pretty much is you have a field and you have a polynomial with coefficients in the field, and there are probably two things that you want to know about this polynomial. Does it factor? Does it have a root in the field? Now, these two questions are related to each other, and what we're going to talk about is which is harder, to figure out whether a polynomial factors in your field or whether it has a root in your field. Okay. So, on one hand, we know that if we have this polynomial that has degree at least 2, if it has a root in the field, well then there has to be a factorization. There has to be a split off of a linear piece. So if you know that it has a root, then you know two things. You know it has a root and you know it factors. So maybe determining whether there's a root is harder. But on the other hand, if there's no factorization at all, then there can't be a root. So if you know that it doesn't factor, again, you know two things. You know it doesn't factor and you know it doesn't have a root. So maybe factorization is the harder question. Okay, we're going to be talking about computable fields. The name computable field is a little bit deceptive. The way I think about it is that elements are getting enumerated into your field. Rational things, mostly these are going to be extensions of the rationals. What I mean by computable is that given any two elements that you know are in the field, you can find their sum or their product. So the addition and the multiplication, those are what we call computable functions. And I'm actually going to define computable functions soon. So some examples of fields which we could call computable fields. There's a way to present them computably. The rationals, the algebraic closure of the rationals, finite field, anything finite we always say is computable. Finite algebraic extensions of the rationals as well. Okay, a little bit of background.
Excuse me. Could you give me an example of something that's not computable and say roughly why it's not computable?
Are you familiar with the halting problem? So I could define a non-computable field based on a classic non-computable set. Say, so you have this classically non-computable set, and into my field, along with all the rational things, I'm going to put in the square root of the nth prime for every n which is not in my classically non-computable set.
So that's an infinite algebraic extension.
It's an infinite algebraic extension, and I don't even know, well, I don't know exactly what's going in there.
Right.
You know, it depends on, I don't know, things sort of fall out of the field rather than being put into it.
It's an extension, only its mother could love.
Okay, so we call a function computable if there's if there's a Turing machine which computes it, we say usually it's Turing computable. Sometimes the functions are partial functions, meaning it may not converge on a particular input. Maybe it converges on 0, maybe it doesn't. Maybe it converges on 1, maybe it doesn't. And then once we have the definition of computable function, we can say whether a set is computable or not. A set is computable if its characteristic function is a computable function. A few facts about computability that we're going to use kind of subtly. So this classically non-computable set that I mentioned, sometimes denoted by K, it's a computably enumerable set, but it's not computable. Meaning if you name a natural number, I can't tell you whether or not it's in there, but elements sort of just, they drop in their image of the partial computable function, so if the partial computable function converges on 0, okay, well then the image goes in. If it doesn't converge on 0, then nothing will go in for there. And then same thing for 1, for 2, for 3, and so on. Computable bijections, these are just quick facts. There's a computable bijection from the naturals into pairs of naturals, and also a bijection from the naturals into arbitrarily long finite tuples of naturals. We're going to use both of those facts. Okay, so this is specific to computable fields. So we define the root set of a field to be the set of polynomials with coefficients in the field which have roots in the field. So the root set is a set of polynomials. The splitting set is also a set of polynomials. It's the set of polynomials with coefficients in the field which split. And when I say split, I don't mean necessarily split into linear things, like in the term splitting fields. I just mean that it factors non-trivially. So that's another set of polynomials. It turns out that if we know which polynomials in the field split in the field, we can determine which polynomials have roots. So we say that the root set of the field is Turing reducible to the splitting set. Meaning if you have knowledge of the splitting set, if you have, say, an oracle for the splitting set, this all-powerful splitting set being that you can ask, does my polynomial factor in the field? And he has to give you the right answer. So here's a quick example of how this might work. You have a polynomial and you want to know whether it has a root in your field. And so you ask the splitting set, does it factor? And the splitting set says, yes, it factors. Okay, it factors, fine. So now I'm going to go look through all the polynomials. They're enumerated. I can look through the polynomials with coefficients in the field until I find two of them that multiply to the one I started with. So I find my factorization. And then I go back to the splitting set and I ask him, well, do these factor? And I can keep asking him as I factor, if he keeps saying yes, whether these pieces factor further. And if I end up with something linear, I know there's root. If the splitting set says no before I end up with something linear, then I know that there's no root. Here we go. Okay, so we use this notation to say that the root set is Turing reducible to the splitting set, or we also say the splitting set computes the root set. So the phi, that's a Turing function with an oracle. The oracle is the splitting set. It happens to be the ETH oracle, Turing function with the splitting set oracle. And this is the characteristic function of the root set. So there's a Turing machine that uses a splitting set oracle and will compute the characteristic function of the root set. How about the other way around? if we had an oracle instead for the root set, could we compute the splitting set? And even though I'm not going to get into the details, because this really isn't the meat of what I'm going to talk about, it turns out the answer is yes. You can compute either set from the other. We call them Turing equivalents, because each one is Turing reducible to the other. So given one of these sets as an oracle, there's a Turing machine that will compute the other. Okay, so if they're Turing equivalent, is there any other way to distinguish their complexity? Can it still be true that one of these sets is harder to compute than the other? And it turns out that there are plenty of other reducibilities, not just the Turing reducibility. Turing reducibility is a very coarse way to measure difficulty. If we use a finer measure, maybe we can find a way to separate out the difficulties of these. So I'm going to be talking about two measures of difficulty that are finer than Turing equivalents, and here's the first one. So this is a very strong way to compare two sets. So a set B will be one reducible to some other set C if there's a total, not just a partial function, but a total computable and one-to-one function, such that for every natural number, the natural number will be in B if the function evaluated at that natural number will be in C. This notion of reducibility is so strong that if B and C happen to be equivalent under this reducibility, if they're one equivalent, we say that they're computably isomorphic. So it's like saying B and C are just about the same thing. Okay, so we were talking about the root set and the splitting set. So we're going to compare the root set and the splitting set with this one reducibility. So it turns out that if F is a computable algebraic field, the splitting set, 1 reduces to the root set. In other words, under this reducibility, the root set computes the splitting set. So technically the root set is harder, or at least as hard. However, there is a computable algebraic field where we don't get the one reduction the other way. So one reducibility actually tells you that, yes, the root set is harder to compute. Just a little bit harder, because they were Turing equivalent, after all. They sat in the same Turing degree, but they don't sit in the same 1 degree. Okay, there is a third reduction that I wanted to describe, the bounded Turing reduction, which is similar to the Turing reduction, except there's a computable bound on how much of the oracle set you're allowed to use. So B is bound to Turing reducible to C. If B happens to be, first of all, Turing reducible to C. But there's a computable function, F, I guess, such that the computation is only allowed to ask questions of its C oracle of elements that are below, well, less than or equal to F of X. So before you ask a question of C, before you ask C whether or not he contains a particular element or not, you have to know how far out you're allowed to go in C. Are you going to be able to ask C about the 100th element, about the 1000th element? Sometimes this reduction is called the name that tune reduction. A long time ago there was this show on TV called, it's a game show called Name That Tune, and the contestants had to be able to say, before they heard any notes of the tune, how many notes they would need to identify the tune. So this is sort of what's going on there. And this is how the three reductions relate to each other. So the strongest one is the one reduction, and the weakest one is the Turing reduction, and the bounded Turing reduction sits in the middle. So the question is now, the root set and the splitting set were equivalent under Turing reduction, and they were not equivalent under one reduction. So it's sort of left open about what happens under the bounded Turing reduction. I mean, it's weaker than the one reduction, so maybe they are equivalent, but it's stronger than the Turing reduction, so maybe they're not. So one direction looks like this. If you have a computable algebraic field, then its splitting set is bounded Turing reducible to the root set. Why is that true? Well, on the previous slide, we saw that if f was a computable algebraic field, then the splitting set is 1 reducible to the root set. Well, if we have a 1 reduction, then we have a bounded Turing reduction in that direction. And the other direction pretty much says that bounded Turing reduction behaves more like the 1 reduction with respect to the root set and the splitting set. It does distinguish the complexities of these two things. There is a computable algebraic field where the root set does not bounded Turing reduce to the splitting set. So again, the complexity of the root set is just a little bit harder. Okay, the reason why these two things happened, why we had a bounded Turing reduction in one direction but not in the other direction, was based on something that I called the crucial algebraic fact. Okay, so my fields F0 and F1, they all sit under this big Galois extension of Q. Not really important that it's a Galois extension, they all lie in the same neighborhood. And so here's the statement. For every polynomial with rational coefficients, F0 and F1, the fields, contain roots of exactly the same rational polynomials, meaning F0 has a root of a polynomial if and only if F1 has a root of the same polynomial, if and only if F0 and F1 happen to be isomorphic. So under some automorphism of the Galois group, it'll take one of those fields to the other. So, okay, saying that in easier words, F0 and F1, the fields, they contain roots of exactly the same rational polynomials if and only if they're isomorphic. And it's a true statement. So now I want to ask you, what happens if I take the root sets, R sub F0 and R sub F1, and instead replace them with splitting sets? The statement would read as follows. For every rational polynomial, the polynomial splits in F0 if and only if it splits in F1, if and only if F0 and F1 are isomorphic. So in other words, F0 and F1 split the same rational polynomials if and only if they're isomorphic. Is it still true? It worked for the root set. Anybody? No? Okay. So it turns out that if you replace root sets with splitting sets in this statement, it's not true anymore. And this is kind of significant. So the first example that ended up popping out at me was this one. If you take the rationals and you adjoin, say, the 4th root of 2 and the square root of -1, and then if you also consider the rationals and adjoin the square root of 2 and I. These two fields can't possibly be isomorphic. One is a proper subfield of the other. They have different degree over the rationals. Yet, given any polynomial with rational coefficients, it either splits in both or it doesn't split in either. So these are two non-isomorphic fields which do happen to split exactly the same rational polynomials. I did need to generalize this example a little bit because I ended up needing infinitely many such examples. So it ended up looking something like this. If you take your field f0 to be the rationals adjoined with a primitive p squared root of unity, where p is prime, and then f1, you take the rationals and you adjoin the sum of that element and its inverse in the group of p squared roots of unity. F0 is the bigger field. It properly contains F1, so they can't possibly be isomorphic. But just like in this case, they will split the same rational polynomials. Any polynomial with rational coefficients either splits in both places or in neither. I don't think there's anything else I specifically wanted to say about that. Okay, so the point was to build a computable algebraic field where there is no Turing reduction from the root set to the there is no bounded Turing reduction from the root set to the splitting set. So what exactly needs to happen if we don't want a bounded Turing reduction from the root set to the splitting set? And the notation here is a bit technical, but I'll explain. So for every e and I in omega, we have the requirements. Well, for each e and I, there's a different requirement. So we have this rational polynomial with rational coefficients. If you take this polynomial and you plug it into the ith partial computable function, and if that happens to converge, once that converges, and you take the eth Turing functional with oracle, not just the splitting set, but the splitting set restricted. Remember bounded Turing reduction? Splitting set restricted to whatever this number was, whatever it converged to. And you plug the same polynomial in to see if it converges on this polynomial. If they both happen to converge, we want the splitting set to give us the wrong answer. We want the splitting set, the restricted splitting set oracle, to give us a 0, meaning, no, this polynomial doesn't have a root in the field, when in fact we're going to put one in. So somehow we're going to be able to trick the restricted splitting set oracle into saying, no, your polynomial doesn't have a root, when there really is going to be one. Okay. Now, the difference between fields like these is only with the polynomials that have rational coefficients. So we want to make sure that once we restrict the splitting set, that the initial segment of that splitting set that we're looking at only has rational things in it, polynomials with rational coefficients. If they only have, if they're only polynomials with rational coefficients that we're looking at, then the splitting set can't tell the difference between fields like these. The splitting set sees that, well, it contains polynomials that either factor over both or factor over neither. But the root set can tell the difference because the root set will say that, you know, for this field, I've got this polynomial, I have a root of this one, but this field won't have one. Okay, so we build a field by adding elements, algebraic things over the rationals. So here's what's going to happen. Remember I said something about a p-squared root of unity? So we're going to choose a prime, p. The equivalent to 1 mod 4 part I can explain afterwards. It's a little bit technical, but it didn't work with the ones that were congruent to 3. So let's take a primitive p-squared root of unity for this prime and adjoin it to the rationals, and then take a look at the lattice of subfields that it makes over the rationals. Okay, what polynomial are we going to pick? Well, we're going to pick the polynomial whose roots are exactly the primitive p-squared roots of unity. It's called a cyclotomic polynomial because its splitting field is called a cyclotomic extension. Okay, so what happens? We take the polynomial q, and we feed it to little phi sub I, and we wait. And if it never converges, if it never halts, then we don't do anything. It's not going to matter. But if it does converge to something, say, okay, well, at stage S0 of the computation, it halts. So we move to step 1. And what we do is we take this element, the sum of the primitive p-squared root of unity and its inverse, and we enumerate it into the field. We enumerate it into the field in such a way that the first this many elements of the field will be rational. If the first so many elements of your field are rational, then the first that many polynomials that are enumerated will only contain rational coefficients. So here's what's happening. So here's the rationals. Here is... this part's kind of funny. I can't really draw a zeta. So, yeah. So I just draw z's. Because I mess up zetas and then I get laughed at by people who speak Greek. Okay, so here's the whole cyclotomic extension, and down here, here's the rationals. So if we get convergence on this, we add this element to the field, and it generates all of this. I mean, we had the rationals all to begin with, and then the field grows by quite a lot when you put this element in. Okay, once we've done that, we're going to go to the second Turing computation, the one that has the restricted splitting set oracle. So the result of the first computation is right here. The splitting set is restricted to whatever that number is. You can only go that far. And again, plug in the same polynomial and see what happens. If it never converges, we don't do anything, and our field stays like that. If it does converge, well, there are 3 possible outcomes of this convergence. Maybe it converges to 1, which is an indication that the splitting set says, yes, your polynomial has a root in the field. But the polynomial that I picked had the primitive p-squared roots of unity as its only roots. Those all lie over here. They're not in the field. So if he converges to 1, he messes up right away. He says there's a root when really there isn't. If there's convergence to something other than 0 or 1, we take this to mean a nonsense answer. He's supposed to give us back a yes or a no. If he gives us back something different, we do the same thing as we would in case 1, nothing. The potential problem is if there's convergence to 0, because this is an indication that the splitting set, the restricted splitting set, says that no, there's no root in the field. And as of right now, he's correct. There isn't a root in the field. So what are we going to do? We put one in. So we add one of the primitive p-squared roots of unity to the field, and that generates the rest. Okay. So he said there was no root, and we put one in. However, when you add something to your fields, you're probably also adding things to the splitting set of the field. And we're using the splitting set as our oracle. And if the oracle changes, the computation starts all over again. And if we're in case 3, and the computation starts all over again, and then later converges to 1, we're screwed. Because we already put a root into the field. We can't take it out. And now the splitting set says, yes, there's a root. There's nothing we can do. So somehow we have to justify putting this root in and not changing any of the oracle. So how do we know that it won't mess up the oracle and restart the computation? It was back to that fact a few slides ago that this field and the big one, they split exactly the same rational polynomials. The splitting set was restricted to a particular point where everything below the bound was a polynomial with rational coefficients. So anything in there that was going to split in the big field already split in the smaller one. So there wasn't any change in the oracle. This is, in symbols, what I'm saying. At stage 1 and at stage 3, these things are the same. Nothing changed. So the rational part of the root set can tell the difference between the two fields, but the rational part of the splitting set can't. So the root set really does have more power than the splitting set in that way. This is still my favorite example. The root set can tell the difference between them, but the splitting set can't. Okay, so the next issue is that, remember the slide with the requirements on it? So we had R sub EI. So for each E and each I, we had a different requirement. And we need to satisfy them all. Not just one of them, but all of them, all at once. This infinitely many requirements means we're going to be picking infinitely many different polynomials that have these p-squared roots of unity as their roots for different p's for different polynomials. And we need the splitting set oracles for each of the requirements not to interfere with splitting set oracles for other requirements. Here's what I mean. If one requirement says that, so we do this procedure again, and maybe it turns out that that the second computation converges to 1, and so we never end up putting this root into the field. The field stays at half its size. Well, how do we know that maybe if we're working on behalf of another polynomial with roots, primitive p-squared roots of prime for different p, that if we put in a root of that polynomial, it won't generate something that's in here? So this helps us a little bit. If m and n are relatively prime, which they are in our case because we keep picking brand new primes. The only way that two of these egg-shaped field things could intersect is in the rationals themselves. So adding something on behalf of another prime will not cause problems. What can technically cause problems is if you're talking about doing something on behalf of a third or a fourth prime, and you're looking at the field generated by 2 or 3 of these things, elements that sit here are the problematic ones. So what ends up happening is that, and I'm not going to get into this too much, but we say that there's injury that happens. So for example, R00, he's the first requirement. He has the highest priority. He gets to keep stuff out of the field or put stuff into the field, and if that injures the procedure that any lower priority requirement is working on, well then that requirement is going to have to start over with a brand new polynomial with a brand new prime. Okay, so this was just a corollary that's that comes from this, why this works. So this one says there are always new primes to choose that will not interfere with the field that you've already built. So I guess the stuff that you've already built at a particular stage, however many primes you've dealt with so far, call it K. There are infinitely more primes, P, to choose from that don't intersect K. Okay, but the real point was this one. The root set having strictly more power over its rationals than the splitting set does. Being able to tell the difference between 2 fields while the splitting has no idea. Okay, so
We have questions.
So what is the answer to the question?
the answer to the question is
the root
that
was strong in finding
the bounded Turing reduction, just like the one reduction, says that the root set has slightly higher complexity. It has more power.
So, can we develop an algorithm to answer that question? I mean, develop an algorithm that should happen that process?
It depends on what reduction you're talking about, I guess. If we're talking about, say, just the rationals, well, the rationals has a splitting algorithm, or finite extensions of the rationals. They have splitting algorithms. We know exactly which polynomials factor and how.
Is there a way, this is an interesting fun fact, and is there a way to give us a glimpse of the intuition that describes how you discovered, so one field is finer than the other, right? In some sense.
One reduction
Yeah.
is finer than the other?
No, I mean, so these two, they split the same, right? One field is a subfield of the other.
Yes, okay.
Okay, and so how can I see that they split exactly the same rational polynomials?
Okay. There's a proof in my paper. It's algebraically technical, very much so that I wasn't going to present it in a talk where I wanted to emphasize the computability.
Right. But I mean, is there a germ of an intuition you know, a microbe of intuition that I could get. Because it is, I mean, that's curious, right?
Yeah, it is interesting, yeah.
I mean, if the answer is just it's technical, then I guess that's the best we can do. But
It had something to do with the degree of each of the fields over the prime subfield. I don't remember exactly what it was.
I'll just throw out that it looks more plausible if I think of it as saying that a polynomial with coefficients in that one on the bottom that doesn't split but splits over the one on the top has to have at least 1 square root of 2 or I among its coefficients.
In this specific example, that would be true. I mean, this is the example where I first thought that maybe every polynomial that factors here also factors here. I mean, the rational coefficient ones, because I just, I sat for hours trying to find a polynomial that has coefficients in the rationals that factor here but not here, and it didn't work. And so I finally emailed my friendly neighborhood algebraist, and he said, no, of course it doesn't work. They split exactly the same rational polynomials, and here's why. And he produced this entire proof for me that I haven't been able to find in any book ever. So I guess he took care of the very technical algebraic stuff that I didn't understand at first.
No, it's interesting.
Something I was thinking about earlier, the simplest thing that you didn't have on the slide list of things that were computable was, in my mind, was R.
R is not countable.
I see.
We only deal with countable things.
Okay.
Uncountable computability theory is an entirely different realm.
Now, when you said, at one point you defined something as computably enumerable.
Yes.
Is computably enumerable, in some sense, the limit of computable things? I mean, is it like a union? If it's a computably enumerable set, is it the union of computable sets or something? I mean,
well,
is there a way to
union of computable sets, it would have to be a union in a non-computable kind of way.
Okay.
Because if it were a computable union of computable sets,
So
it would
it'd
be
be computable, right?
Right.
Right.
Yeah.
The big deal is that the enumerable one, a computable set you can ask is in or not. An enumerable one you can ask, but the answer is, oh, I don't know, wait a while, see if it shows up.
I see.
And maybe it does, then you know. Maybe it doesn't, then that would just mean you've not waited long enough.
I see. So it's related to the halting problem again?
Yeah. The halting problem is, when the classical example of a set which is computably enumerable but not computable is the halting problem.
Is there anything else? All right, I do want to mention that we will have refreshments up on the 3rd floor in the math department library after the talk, and we're grateful to